All right, Math A, here we go. We've got lesson 3-5, linear function word problems, day 1. Okay, so first type of linear function word problem we're going to look for is a proportional function. Proportional functions are just linear functions that pass through the origin. So their y-intercept ends up being 0. Here we see y equals kx. Usually it's y equals mx plus b. For some reason with proportional functions, they use k instead of m. Maybe k stands for confusing or something. I don't know. But k is just the slope. There is no number over here at the end because it's proportional. It passes through the origin, meaning the y-intercept is 0. Okay, so here's what a proportional function would look like. The amount of lime yogurt that Matthew eats is proportional to the number of weeks that pass. I am Matthew. I like lime yogurt. So anyways, Matthew eats 5 cups of yogurt every week. Okay, we're supposed to identify the dependent and independent quantities. Okay, so we have 2 different quantities in here. We've got the amount of yogurt, it looks like in cups, and we've got time in weeks. So my 2 quantities that I'm looking at are the cups of yogurt and time in weeks. One of those depends on the other one. So if you look at it, the weeks do not depend on how much yogurt I'm eating. The yogurt depends on how many weeks have gone by. So we would say that the dependent quantity is the cups of yogurt. And the independent quantity would be the time in weeks. Now, the dependent quantity is usually our y-axis, and the independent quantity is our x-axis. So let's go ahead and write an equation for this one. We're going to write y equals, and then k is the rate of change. We are eating 5 cups every week. So this is going to be 5 times the number of weeks, which is x. So our equation would be y equals 5x. So if I ate it as my input of x, which is weeks, if I ate yogurt for 1 week, we would plug in 1 here. 5 times 1 is 5. 2 weeks goes by, 5 times 2, because 5 every 2 weeks. So 5 every week, and there's 2 weeks, that'd be 10. 3, we get 5 times 3, 15. 5 weeks goes by, 5 times 5, 25. 10 weeks goes by, 5 times 10, 50 cups of yogurt. 52 goes by, so that looks like, what is that? That's a year. So a year of yogurt. How much yogurt have I eaten? Let's see. We've got 260. Oh, goodness. That's a lot of yogurt. All right, so there's our table. We've got our input, which is our independent quantity, our time in weeks. We've got our output, which is the number of cups of yogurt that have been eaten, consumed. Okay, and now we're supposed to graph this. We want to label the functions. Remember, our independent quantity is going to go on the x-axis, so this is going to be time in weeks. And then on the y-axis, let's flip it around here. This will be the yogurt. And this is the number of cups. Okay, so at 0 weeks, I have eaten 0 yogurt. So there's my first point, the origin. So that's what it means to be proportional, is we're going to pass through the origin. After 1 week, we're going to do 1, 2, 3, 4, 5. After 2 weeks, 5 more. 1, 2, 3, 4, 5. After 3 weeks, 1, 2, 3, 4, 5. So we've got this linear function that is going through the origin. Now, on this particular graph, we would probably connect it because I don't eat all the yogurt all at once. It happens during the week. So we would do this. This isn't completely accurate. It's not like all day I'm slowly eating yogurt, and that's what this line is saying. It's saying all day long I'm slowly eating the yogurt. It might be better to have small little every day eating 1 cup of yogurt or spreading it out. I don't know. For this one, I would go ahead and connect it because I'm not eating 5 cups all at the same time. It's not quite as accurate for the situation, but we're going to just live with it for right now. How many cups of yogurt will Matthew eat in 2 years? Okay, so how many cups of yogurt? That's our y, that's our independent quantity. And 2 years, you have to watch out for your units, and that's why we write down our units here when we label our axes, because this is 2 years. I would not plug in 2 for x, even though x is time in weeks. So 2 years, if there's 52 weeks in a year, so each year is 52 weeks, that would be 104 weeks. So that's my x quantity right there, is I've got 104 weeks. So I would use my equation. I'd say y is equal to 5 times 104 weeks. Let's see, we get 520. So after 2 years, I would have 520 cups of yogurt. Pretty sure that's not healthy. And how many weeks would it take for Matthew to eat 105 cups of yogurt? Now that is the y quantity, that's the independent. How many weeks? That's our x quantity. So in this case, using our equation of y equals 5x, I would plug 105 into y. So 105 equals 5x. And then to solve for the number of weeks, I would divide by 5. And 105 divided by 5 is 21. So it would be 21 weeks. All right, so those are proportional functions where the y-intercept is 0, so it goes right through the origin. Okay, just regular linear functions, we would do it in the form of y equals mx plus b, where b is the value of the starting point a lot of times on these functions, or the y-intercept. So here we go, we hire a plumber to install a new drain. They charge $50 for parts and $100 per hour for labor. The total bill is the function of the hours of labor. So total bill being a function of hours of labor, that is saying something. Is a function means it depends on how many hours of labor. So the bill depends on how much hours that he ends up working. So that's indicating to me that this is the dependent quantity. That's my y variable there. And my hours of labor, that would be my x. Because the bill is a function, or is changed by, or is caused by the hours of labor. So this is dependent on how many hours that gets worked. So my dependent quantity is the bill, the total bill. The independent quantity, and that would probably be in dollars. The independent quantity would be the hours of labor. All right, so now we're ready to write an equation. Well, we know that our y value is the total bill. So, what is made up of the total bill? Well, we know that he's going to get paid $100 per hour. So that would be 100x. $100 for every x value of labor. But then there's more to it. They also have to pay for parts. So this is not dependent on how many hours. That just happens. It's what we call a constant. No matter what, we're going to have to pay for these parts. So that's kind of like the starting value of the bill. We're going to start at $50, and then we're going to add to that $100 for every hour. So this is like the y-intercept, whereas this would be like our slope, the $100 per the hour. Okay, fill in the table. Let's say we didn't work at all. Well, we'd still have to pay for the parts, so we'd still have $50 that we owe. 100 times 0, and then plus the $50. If we worked 1 hour, we'd get $100 from the hour of work plus the $50, so that'd be $150. 2 hours, we got $200 plus the $50 for the parts, so $250. 3, $350. 4, $450. 5, $550. So it's 5 hours would be $500 for the hourly labor plus the $50 for the parts. Okay, so graphing this, we would have labor hours as our independent quantity, and then the total bill would be in dollars, our dependent quantity. So the bill depends on how many hours you worked. Now the hours here we can probably just go, 1 hour, 2 hour, 3 hour, 4 hour. But over here on the graph, look at our numbers that we have to graph. They're pretty big numbers. So maybe on this one, it would be better to change the scale of the graph. So instead of going by ones, if I went by ones, the y-intercept wouldn't even fit on this one. So let's go by 50s instead. So this is going to be 50, 100, 150, 200, and so on. So I'm changing my scale of my graph just so I can fit everything that we need on this one graph. Looks like we make it up to 800 up there. All right, so use your graph. We're supposed to graph the function. Okay, so let's graph the function. So at 0 hours, he got paid 50. We have at 1 hour, it's 150. 2 hours, 250. 3 hours, 350. 450. 550. 650. 750. And then we'll stop right there. Now this one, it does make sense to connect it, because what if you worked half an hour? Would we just not pay him for that half hour? Yeah, we'd still pay him probably for the half hour or a quarter hour or something like that. So that means if he works just a half hour, it looks like if he just works a half hour, he'd get paid $100 for it right there. Because here's halfway in between 0 and 1, and it looks like he would still get paid $100. So we would connect this graph because we could have like just being paid 15 minutes. And this would probably be around 15 minutes right there. So it doesn't have to be full hour calculations here. So we would go ahead and connect this. Use your graph to approximate how many hours would be worked if the total bill was $625. All right, so this is $650. This is $625 right here. So in order to use the graph, probably should have used a ruler, but whatever. Breaking the law. All right, so if I draw a line, everything on this line represents $625. And then if I go down here, that wasn't very straight, but you get the point. So this is 1, 2, 3, 4, 5, 6. It looks like 5.5 hours. That's halfway in between these two, right? So it looks like if we follow our graph down, I really should have paid attention here. Wasn't paying attention. It looks like about 5.5 hours, just using their graph and estimating. So we can see over here, the y value was 625. And then if we go down to what the x value is, it looks like about 5.5 hours or so. So you can use your graph to predict answers. So we think it's approximately 5.5 hours. We could go ahead and use the equation to verify our answer. We could end up plugging in 625 into here and seeing if that's actually what we get. Let's go ahead and do it just for funsies. So we've got 625 equals 100 x plus 50. I would subtract 50 and I would get 575. So I'm subtracting 50 from both sides. And I divide by 100 right here. I'm writing really small, sorry. I end up with 5.75. Okay, so I was off a little bit. My guesstimate was 5.5 hours, but the actual answer using the equation is 5 3/4 of an hour. Okay, so sometimes when we use our graph to find things, maybe it's not as accurate as if we actually use the calculation. There you go. What would the cost of the bill if the job took 8.5 hours? All right, so 6, 7, 8.5. All right, that's off my graph. So I can't really use my graph to prove this one or to disprove it. So let's just plug in 8.5 hours into our equation. Remember, hours was the x, so I'm going to plug 8.5 hours into our equation for the x. So y is equal to 100 times 8.5 plus 50. So here we get y equals 850 plus 50. It looks like we have a $900 bill. So the bill would be $900. So we plug in 8.5 times 100, that's 850, and then plus the $50 for the parts. Last one, if the bill was $975, how many hours did it take to do the job? Okay, so this is bill, which is the y value. How many hours? That's an x value. So we should plug in 975 into the equation that we made for the y value. Here I would subtract 50 from both sides. I'd get 925 equals 100x. And I divide both sides by 100, which would just move the decimal over 2 places. And I would get x is equal to 9.25. So it looks like 9.25 hours. Or we might say 9.25 hours. Or a quarter hour is 15 minutes. So we would say, or 9 hours and 15 minutes. Three different ways we could give that answer. All right, that's all I got for you today. Math hard. I'll see you later. Bye-bye.